have with us Carlos Hernández-Monteagudo. He did his PhD in Salamanca, and after that he moved to MPA in Munich, where he has been working he was working for 3 years with a group of Raziz-Sunyaev. Then he moved to Philadelphia for 2 years and a half, and he was working with a group in the University of Pennsylvania. But also there he started a collaboration with the Atacama Cosmology Telescope, and today he will show some slides about this project, which is aiming to measure clusters at very high redshift using the Sunyaev-Seldovich effect. This year he returned to MPA, where he is now a postdoc, working again in the same group of Raziz-Sunyaev, and today he's going to talk about the problem of missing baryons in the local universe, and how can we try to observe these baryons using the CMB observation.
Okay. So first of all, I would like to thank Rafa and Jose Alberto for the invitation. It's very nice coming to Tenerife, but it's even more nice if it's winter, you're in Munich, it's dark at 4:30 p.m. and you don't see the sun for the whole week because it's foggy, right? So it's very nice. Thanks again for the invitation. So, well, maybe I've been a bit too ambitious in the amount of things that I wanted to talk about. But, I'm going to try to go fast, but this should not prevent you from stopping me at any moment and asking me questions, okay? So this is the outline of the talk, right? I was told to give a big introduction, so I think like 4 or 5 points of those 8 points there are actually introduction to the topic. And, only in the very last half of the talk, or even a quarter of the talk, I would talk about the real topic of it. Right? So, okay, CMB and cosmology. For those who are non-cosmologists, yes, this transparency for introduction. This is our way of understanding. Let me see if here I am. This is how the standard model depicts the evolution of the universe, right? So, the CMB is just a radiation that was coupled to photons at the beginning of the universe. This is the beginning of the universe, and this is the current state of the universe here. And so it underwent through a phase of accelerated expansion that we call inflation. And then, it expanded more moderately, and until the very late ages, where we seem to have evidence of a new accelerated phase of expansion. The CMB is this radiation field that, at early times, when the universe was hot and dense, was coupled to the electrons. But at the moment that the electrons recombined the protons to form hydrogen, then the CMB photons could propagate freely towards the observer. So there is an epoch here where there were no stars, and this is called the Dark Ages. And then, when the first stars arise, ionize the medium again, right? So from an observer today can see all the way back up to the last scattering surface, and we cannot see any further, right? Cosmology is based upon the cosmological principle that says that the universe on the largest scales is very isotropic and homogeneous. And a good proof for that is the fact that the CMB is very homogeneous. So the CMB is this radiation field that has a black body spectrum and that has inhomogeneities and anisotropies of 1 part in 10 to the 5. That is, it's extremely homogeneous. But these small anisotropies have a lot of cosmological value somehow. So I will be showing how to study these anisotropies. This is the way we do it in the CMB language, right? So this is a plot of the power spectrum, of the angular power spectrum, which is nothing but the Fourier transform of the angular correlation function. And this simply tells you what amount of anisotropy you have at the given angular scale. So this L multiple is just the Fourier mode or the Fourier counterpart of the angle on the sky. So this is telling you this was the situation in 1999. So we expect to have a lot of anisotropy or spots in the CMB temperature or in the CMB intensity at a scale of between 2 and 1 degree or so. We have smaller spots or spots of a smaller amplitude at larger scales, at say 90 degrees or something, and then eventually at very small scales, at very high multiple, again the CMB becomes very uniform and there's very little anisotropy. Okay, so this is the evolution. So you see that in 99 the CMB was not able to constrain many cosmological parameters, but now it really constrains the models pretty well. Okay, so there has been an improvement, a net improvement throughout these last few years, but this is not the whole end of the story, because there is still a lot of research. The model, the standard model for cosmology, makes a lot of predictions, and many of these observables affecting these predictions have not been observed yet. For instance, there's a lot of research trying to find some type of the CMB polarization that has not been measured yet. Right? as I said, you have evidence that in the very late stages of the universe, the universe has been expanding in an accelerated way. And what causes this acceleration is not clear, so we are trying to find out what this can be. And this is what this dark energy is about. This dark energy is supposed to be the cause for this accelerated expansion of the universe. Of course, we don't know anything yet about the dark ages. We have not been able to resolve the epoch where the first stars were formed and de-ionized the universe. So all these are chapters in the cosmological history that we know very little about, and we are trying to investigate, to look upon. Of course, from the more theoretical point of view, there are other issues like what is actually dark matter, what kind of particle is dark matter, or what is the field that is causing dark energy from a theoretical point of view. There is also a lot of active research here. But today, I will focus on some issues, cosmological issues, that are affecting the predictions of the theory at low redshift. And these are the Ball flows and the missing baryons. This is what I'm going to talk about today. Okay? So the issue of Ball flows. So the theory describes in a statistical way how the universe, despite of being very homogeneous, has small clumps of density, and these evolve upon the action of gravity in an expanding universe. So the theory describes how these density perturbations are distributed on the space in the universe, and how they grow up, and how these matter clumps actually move due to the action of gravity, right? So make predictions, the theory makes predictions on the density distribution and on their velocity, their peculiar velocities. And here I would like to remark the difference between peculiar velocity and Hubble flow. In an expanding universe, where x is a fixed moving coordinate, you have that the universe is expanding according to a given scale factor a, where the derivative is positive, so it's growing up. The universe is expanding. So the deviation from the pure Hubble flow is what we call peculiar velocities. And the source of this peculiar velocity is gravity. And the theory makes neat predictions about these peculiar velocities. So on the density side, it's not so difficult to test the theory because we can observe galaxies, and we can assume that density and matter is traced by galaxies. So the theory makes a prediction on what is the amount of anisotropy at a given scale. So sorry, you cannot see it very well. This is the power spectrum for the density fluctuations. And this is telling you, again, the amount of anisotropy, the amount of clustering, the amount of clouds of galaxies that you have at a given linear scale, at 1 megaparsecs, at 10 megaparsecs, at 1,000 megaparsecs. The linear theory makes the solid line prediction. And then you have observations, which you can compare to the theory. And that is cool, right? But at the same time, the theory makes predictions on the peculiar velocities. But we have no data, because we cannot observe peculiar velocities. Distinguishing peculiar velocities from the Hubble flow is really tough. So we know practically nothing about whether this power spectrum is correct or not. Okay, at least in the low redshift universe. So this is one issue. The second issue I would like to talk about is about the missing baryons, right? So again, this picture about the evolution of the universe. You have recombination here. This is when the CMB becomes released and starts to propagate freely. Sorry, I'm not very good with this mouse. And then, so there's some region here where the universe is neutral, but then it's reionized again because of the appearance of the new stars, right? So at these stages, at later stages, the universe is far bigger, and it's ionized. It's transparent to radiation, right? So it's hard. In these later stages, it's much harder to find baryons because here the universe is much bigger and much less dense. So this is a plot showing the ratio of the baryons seen at low redshift compared to the baryons seen at recombination at the epoch where the CMB was released at redshift 1050. So this is the amount of baryons we see at recombination, and this is the total amount of baryons that we see at redshift below 2. So we barely see like half of them. There's a bunch of baryons that we don't get to see. So where are those baryons? When people run hydrodynamical simulations of the universe, they see that most of the baryons are actually in a low diffuse, in a hot but diffuse phase that does not collapse, does not form stars, and therefore it's very hard to keep track on. Okay, so we have a few handles on these missing baryons. I mean, there are a few tools or there are a few windows that may hope to have some insight on how these baryons are distributed. One of those is the metal absorption lines along some quasars and blazars. So if you have some objects, very bright objects at a high redshift, like redshift 1, some people have claimed that when these objects are in a high space, in a very luminous space, they have detected some absorption lines corresponding to metals like oxygen-7 that are not only located at redshift 0, but at redshift 0.11, redshift 0.02, 0.03, and so on. So people claim that these absorption lines are due to metals that are in filaments, in this fraction, in this diffuse phase of the missing baryons, that are actually intervening along the line of sight. But you see, there are few objects that are so bright that enable the measuring these very weak absorption lines. So this method somehow is kind of limited because you have just a finite set of bright objects along which you can hope to see these absorption lines. Another window to see these missing baryons is actually the X-ray. So if these baryons are ionized and are hot, then the electrons are accelerated and then they are emitting Bremsstrahlung radiation. So they emit in the X-ray, in the soft X-ray. So people have used the X-ray observations looking through the Logman hole, which is a region on the sky which is particularly clean of the emission of the X-ray of our galaxy, our own galaxy. And there they have seen, after they remove the point sources, they seem to see some evidence of filamentary structure, which should be assigned to these missing baryons we know very little about. But all these windows are very limited. It's just like, we have a hole here through which we can see a little bit. We have a few blazes along the line of sight of which we can hope to see some absorption lines, but we don't really have a handle of the total amount of baryons that we are missing. So that's a problem, right? And this connects to the question that Rashid Sunyaev got from Feldovich back in the 60s, and this is, if we wanted to see a cloud of electrons in space, how could we see it? Is there any way to see this cloud of electrons? And indeed, there are different channels of interaction of the CMB photons that fill the whole space with electrons, right? The first of them I'm going to describe is the Thompson scattering. Thompson scattering is just the scattering between one CMB photon and an electron in which there is no energy transfer. Imagine that they are both in the same, they're in thermal equilibrium, so it's just that the photons change the direction, but there's no energy transfer. Therefore, in this scattering, the relative change of brightness is just caused by the peculiar velocity of the cloud with respect to the CMB. If the cloud of electrons is at rest with respect to the CMB, you have as many photons being scattered along your line of sight as the photons that were along your line of sight and they're scattered away. So if the cloud is at rest, there is no way to see this cloud. But if the cloud is moving with respect to the CMB, then all photons in the same way, regardless of their frequency, are experimenting a kick from the electrons, right? And this is the so-called kinetic Sunyaev-Feldovich effect. I have to remark as well that this Thompson scattering is anisotropic. That is, the polarization mode that is, the intensity mode that is oscillating in the plane of scattering is suppressed by this factor. Okay? So, because of this anisotropic nature of the Thompson scattering, if the CMB at the moment of scattering has some quadrupole, is not isotropic but has some quadrupole, then Thompson scattering also introduces some linear polarization. And this is good, because then we can look at the polarization of the CMB, and then we can look at these tiny brightness temperature fluctuations which are caused by the peculiar velocities of the scatterers. I want to remark that these effects affect all photons, all CMB photons the same, regardless of their frequency. And therefore, they preserve the black body spectrum of the CMB. Okay? This is a big difference compared to the thermal Sunyaev-Feldovich effect. This is almost the same mechanism, but in this case, there is an energy transfer. In this case, the hot electrons in a cloud, in a cluster, for instance, are actually heating up the photon. You have a low energy photon that is hit by a hot electron, and then you have a more energetic photon. So in this case, low energy photons, that is low frequency photons, absorb more energy than high energy photons, right? So you have a change in the brightness, a relative change in the intensity of the CMB that actually depends on frequency, okay, in a very definite way. And also depends on the relative in the temperature of the gas, of the electron gas you have here, right? So in reality, this thermal Sunyaev-Feldovich effect is the same as before, which is the density times the length of the cloud and so on, times the temperature, and then some frequency function. So I remind you, yes, that temperature times density is pressure in an ideal gas. So in practice, at the end of the day, we have two effects. The Thompson scattering that does not depend on frequency, but depends on the peculiar motion of the scatterers. Then we have the Compton scattering, or the thermal Swinjaya-Zeldovich effect, that depends on frequency and is also proportional to the integrated pressure, electron pressure along the line of sight. And also have the issue on polarization. This linear polarization is introduced by Thompson scattering whenever the CMB has some quadrupole, has some anisotropy, intrinsic anisotropy. Okay? So these are the three channels with which the electrons, the missing baryons, might interact with the CMB. Okay? The thing is that in the long redshift universe, the sources for these effects are usually associated to galaxy clusters where temperatures and densities are high. But however, galaxy clusters obtain a small angle on the sky. And usually, so far, the studies of the CMB, the measurements on the intrinsic CMB anisotropies, here I'm displaying the map, the CMB map provided by WMAP, is on much larger scales. So this is the power spectrum of this map, right? And it's ranging from scales of the whole sky, like 180 degrees, up to a few tenths of a degree, okay? The physical mechanisms giving rise to these temperature anisotropies are, on the one hand, the Thompson scattering I just described above, right? During recombination, there is a thermal equilibrium between the photons and the electrons, and therefore there is no thermal energy. They are in thermal equilibrium, and there is only Thompson scattering. And also, you have other anisotropies due to a gravitational redshift. The fact that in the moment where these photons were last scattered, they had a different potential. They were in a different potential world than our own potential world. So this difference in the gravitational potential is introducing some further anisotropy that is affecting all photons in the same way. Okay. Also, you have some time change in the gravitational potential. This introduces a new fact, a new effect. I just want to stress that in the largest scales that WMAP is measuring, you have these two effects: the Thompson and the gravitational redshift. But this is, as I said, large angular scales. The maximum angular resolution is of the order of 0.2, 0.1 degrees. But if we want to see the previous effects, if we want to see the thermal Swinjaya-Zeldovich effect, the kinetic Swinjaya-Zeldovich effect, and so on, then we have to go to the smaller angular scales. We have to be sensitive to smaller angular scales. And this is one of the motivations for these third-generation CMB experiments, like the Atacama Cosmology telescope. Right? So what is the motivation? So here I'm going again. So this is a plot of the power spectrum, the intrinsic power spectrum generated during recombination. We want to see we want to confront the model at very small scales in the first place. We want to see whether this is true or not. But also, we want to see all these secondary effects about the kinematic and the thermal Swinjaya-Zeldovich effect that arise also at the smaller scales, at the high multiples. Sorry, you cannot see it very well here, but this is corresponding to the smaller scales. Why are we so interested in these secondary effects, in these effects that take place in clusters of galaxies, like the thermal Swinjaya-Zeldovich effect? So, and here I make a parenthesis. As I said before, there's evidence that the universe is undergoing currently an accelerated expansion. We are in an accelerated expansion phase. The growth of the universe is accelerated. So, if that is the case, this accelerated expansion is affecting the growth of these galaxy clusters. Galaxy clusters are the largest visualized structures in the universe, right? So, they just collapsed. So, if the universe started to accelerate a bit earlier, then the number of these objects that was formed was smaller. That is, the abundance of these objects, the number of objects that you can find when you look at high redshift is strongly dependent on when the universe actually started to accelerate, right? So if we look and we make a census of these objects at high redshift, we will be able to tell whether the universe started to accelerate earlier or later, or what is the equation of a state. It will tell us a lot about this model. Okay? And of course, in these smaller scales, there are also other secondary effects. When the first stars ionize the universe, there are new effects that are arising at the smaller scales, and we're interested in those. Also, this is the ballpark for some other exotic physics like cosmic strings and so on. They should all leave some signature here. So we really want to look at the smaller scales of the CMB. And yeah, so this is one of the motivations. There are a few experiments trying to measure this. This was the sketch for ACT, like at the beginning of the project. So ACT must have a good angular resolution, 1 arc minute, high sensitivity, like 1 microkelvin per beam, which is pretty good compared to previous experiments. And then you have different channels which help you to distinguish the thermal Swinjaya-Zeldovich effect that depends on the frequency from all other effects that do not depend on frequency. Okay. So this was the sketch of the telescope. This is what the telescope looked like at the beginning of last year. This telescope is placed in Cerro Toco, which is in the Atacama Desert, so close to Bolivia, Paraguay, but in Chile still. And it's not far from, actually, from the ALMA from the location of ALMA. The ALMA interferometer is going to be placed here, not too far from San Pedro de Atacama, which is somewhere here. Sorry, I'm not really good with this. Yeah. And ACT is going to be nearby. Okay. So I think I'm going to skip the scanning strategy of ACT, and I'm going to properly address the core of the talk. Right. So I'm coming back to the motivation. We want to probe missing baryons and bulk flows with the CMB. Is it possible? Is it not possible? Can the new experiments, third generation CMB experiments, help us in this search for the missing baryons? So this is one work I did a couple of years ago, where we were trying to find out to what extent the thermal Sunyaev-Feldovich effect will help us in finding the missing baryons. Right? So as I said, the thermal Sunyaev-Feldovich effect is just the pressure integrated along the line of sight, which is just the derivative with respect to R of this Comptonization parameter, right? So the emissivity for the Sunyaev-Feldovich effect. So first of all, I want to remark the Sunyaev-Feldovich effect along a given line of sight is just the Comptonization parameter times a frequency function. I don't care about at this moment, right? But this frequency function is well known. So this acts like a emissivity, right? So if this Comptonization parameter is just an integral along the line of sight, you can see that pressure, which can be seen as an emissivity of this effect that you're looking at. And the luminosity is just a volume integral of the emissivity. Somehow, that what I want to look, I mean, at the end of the day, what I want to know is, where are the sources of pressure? I mean, are the missing baryons in regions where pressure is large, so that they give rise to a large thermal Sunyaev-Feldovich effect, or not? That's what we wanted to know. What is the effect that the missing baryons give rise to in terms of the thermal Sunyaev-Feldovich effect? And what we did is just use one hydro-cosmological simulation, and we placed an observer in the middle of the box, and we sought different lines of sight, trying to find out what is the Comptonization parameter or the thermal Sunyaev-Feldovich along these directions. And what you can see here is that, okay, you can probe all the baryons a priori. You can see the biggest clusters, you can see the smaller groups, you can see the filaments, and so on. Okay, but you're actually interested in the missing baryons. The baryons that are not placed in galaxy clusters, the baryons that are outside the clusters and the known galaxies. So this is the diffuse phase you're after, right? So the question is, will future experiments be able to see this diffuse phase? Well, the question is, the answer is not very promising. Sure. Well, in the simulation, I was just removing along the line of sight integration. I was removing all cells falling within the halos. So I had a simulation. I had identified the halos, the galaxy clusters, and the groups. And when I wanted to do this diffuse projection, I would just ignore those cells, those particles that were within the halos. Right, I agree. And actually, it also depends on the particular resolution of the box, because we were only to resolve halos that were more massive than 10 to the 12 or something. So you might expect that you are going to have smaller halos, like galaxy-sized halos in this map as well, that were not resolved. Right? But in any case, this introduces the fact that you don't resolve the halos, introduces a small correction to the final results. And the final results are this. These are just that we are looking here. So this is just sorry. Let me see. I think I can do it better from here. This tells you the amount of total mass, the fraction of total mass that is in regions with an overdensity bigger than a given threshold. Okay. So this red line is kind of giving the limit between halo and non-halo, collapse structured and non-collapse structured. So what you see here is that 20% of the mass is actually in collapsed halos. But at the same time, this 20% of the mass is giving rise to like 75% of the total thermal Sunyaev-Feldovich effect. That is not good, right? Most of the pressure is actually located in halos. So the thermal Sunyaev-Feldovich effect is not very sensitive to the gas that is outside halos. If you work out the numbers, you find things that are even a bit slightly worse. So 50% of the total matter, of the total baryons, are in regions which are less overdense than 10, right? And they give rise only to 5% of the total luminosity. So in this sense, the thermal Sunyaev-Feldovich effect is not going to help us in finding the missing baryons. But because they are correlated to the halos, then the pressure, the thermal Sunyaev-Feldovich effect, is going to be strongly correlated to the number density of galaxies, right? And this is what we are showing here. This plot shows the cross-correlation, the tight cross-correlation between the pressure, the thermal Swinnerton-Lewis effect, and the number of galaxies. And this can help in actually establishing a link between pressure and galaxy formation and galaxy population. And this connects as well, and this seems to be confirmed by the group here in the ISE, where, if I recall correctly, you've seen that. So these people are claiming that they have found maybe the first group in the thermal SC. So this is a detection of the thermal SC with a very small array. And there's some excess of some decrement that is assigned to the thermal Swinnerton-Lewis effect. And they seem to find some slight overdense, some overdense in the galaxy density, if I'm not mistaken, right? So, things are pointing along this direction. But the bad thing, anyway, is that the thermal Swinnerton-Lewis effect will not help us proving the missing baryons, right? So what about the Thompson scattering? Because we have another channel of interaction. And this was the Thompson scattering. So this is a work that I just finished with Shirley Ho. I'm trying to write it up. And what we did is again, cosmological perturbation theory, trying to find out where is the actual kinetics of the Lewis effect. The Thompson scattering effect on the CMB, when you take into account the velocities of the baryons and the first order in the homogeneities, in the distribution of electrons, right? So this is a second order quantity because this is one order quantity times one order quantity is a second order quantity. So in perturbation theory, you just work out what is the power spectrum, what is the total effect of this density inhomogeneities times velocity inhomogeneities. Right? There are many equations I want to skip. I just will focus on the results, and the results are this. You can properly see them. But in the small angular scales, in the high multiples, we have new power coming here. So we have some prediction of what the kinematics of how the missing baryons are going to influence the CMB. Okay. The thing is, the CMB, the intrinsic CMB, is way larger than this secondary anisotropies due to the KSE. So can we detect the missing baryons? Can we detect the bulk flows of the missing baryons if the amplitude is so small? So this is the problem we have been looking at. And, and there is some hope. There is some hope, though. So in the future, there will be a lot of surveys which are going to provide, which are going to measure, practically I'm going to find all galaxies about a given luminosity limit from redshift 0 to redshift 1, 1.2 or so. So they're going to prove a large volume of the universe. So they're going to provide an accurate estimate of the density field in this large volume of the universe. So if you know this, and if your theory is correct, you can invert the density field into a velocity field. So given a galaxy survey, you can produce what the velocity field of this galaxy survey is going to be. Therefore, you can produce a template, an estimate of what the peculiar velocities are going to be. And you can cross-correlate this template with the actual CMB data that you measure. But this CMB data is going to be the addition of everything. It's going to be the addition of the intrinsic CMB that is coming from the large scattering surface, which is far bigger, plus the addition of these secondary effects due to the bulk flows of the missing baryons. What I want to say is to unveil this small component from the total contribution. Right? Can it be done? Well, you can compute what is this cross-correlation. If you have a good template of the peculiar velocities built upon from your density field that you obtain from your large-scale structure surface, then you can compute this cross-correlation, and you can see whether you have seen this cross-correlation can actually be measured or not measured, right? This is the noise, the uncertainty, and this is the actual cross-correlation. So what we found is that indeed you can, right? So if you add the amount of signal that is coming from different angular scales, you see that most of the signal is coming from the smaller angular scales. But at the end of the day, you may obtain a signal-to-noise ratio of the order between 10 to 100. If you are able to predict from your density surface what the peculiar velocity will be for all halos more massive than 10 to the 14. If you are able to do it only for the most massive clusters, like 10 to the 15 solar masses, then your signal-to-noise ratio is going to decrease. But a priori, this cross-correlation, this will allow to test the theory. If your density field that you measure with your galaxy catalogs is inverted correctly, and the theory is correct, into a velocity field, you can cross-correlate this theoretical density field with the total CMB anisotropies, and this cross-correlation should tell you whether your theory is correct or not correct. So at least we are testing the bulk flow theory. We are testing the theory in terms, yeah. Mm-hmm. Mm-hmm. Yeah.
Highly nonlinear regime. So I wonder,
Right.
and so part of the question is what is the maximum, what redshift is the maximum contribution of all these effects? Is it so near to us that you can?
No. It's
And so how are you going to use an overdensity that you measure locally
No.
and extrapolate it down?
I get your question. I'm talking about large-scale surveys that are not dying at redshift 0.1. I'm talking about punished stars. I'm talking about much deeper, like in the future, okay, like in the next 10 years, there are a lot of surveys planned that are going to be very deep, up to redshift 1.1, 1.2, right? And they're going to be very complete. They're going to have like 100 million galaxies or so, right? This is the type of galaxy surveys that I suggest using in order to invert and obtain the peculiar. Part of them, so this, part of them is coming from redshift below 1, right? So this, the previous plot I saw before, let me see. This effect I saw in the right panel, most of it is coming below redshift 1. Okay, so a priori, the sources for this anisotropy should be probed by these future galaxy surveys. Okay, so this is actually the signature we're trying to find. But you're right, you need them to be deep, right? If you just use 2 mass, for instance, the contribution to the total signal of 2 mass, of the galaxies probed by 2 mass, is negligible. Forget about it. You have to go up to redshift 1. You have to have a huge cosmological body. That's the thing. So a priori, if these surveys provide a decent density field, one should be able to test the bulk flow theory, and one should be able to test whether this correlation exists or not. However, let me remark one thing. The linear theory states that in a given cloud, that the peculiar velocities are correlated in a spheres of around 20 megaparsecs. That means that within a 20 megaparsec sphere, the very brightest, largest clusters are moving in the same way than all the surrounding matter. Okay? All the surrounding matter. So the thing is, can we detect the signature of not just the clusters, but if we just mask out the clusters, could we detect the signature of the surrounding baryons? If we just, in the CMB map, mask out the clusters, that is, mask out the effect in the bulk flows of the baryons that we already know. So we did that exercise too. What would be the signal of the cross correlation if we mask out the most massive clusters? And what we obtain is a worse result. Of course, the signal is much smaller. It's not impossible, but it's not very good. For instance, for a perfect experiment, and I'm assuming that ACT has negligible noise, like this is nominal sensitivities, but in practice we are not achieving this. We have like a 5 signal-to-noise ratio of 5 in the whole sky. So this is very, very, very marginal. That is, probing the effect of the missing baryons on the bulk flows is marginally detectable, but it requires having an ACT-like CMB experiment that is actually covering the whole sky, and this is not the case right now. Right. So, something good and something bad. A priori, this procedure will let us know about the bulk flows, but it's not likely to tell us about the missing baryons. And finally is the part 3 of the talk, which is, okay, but at the same time, this Thompson scattering by the most nearby baryons are also introducing some contribution to the mode polarization of the CMB. Can this help us? Again, same transparency, right? So these baryons, the fact that all baryons surrounding clusters are moving the same way, and all of them are introducing an E mode, a contribution to the E mode of the CMB polarization. So the thing is, if we measure the total E mode of the polarization and we cross-correlate it to the temperature anisotropies caused by the largest clusters, could this cross-correlation tell us about the baryons that are actually surrounding these most massive clusters and actually contributing to the polarization as well? And again, we computed this. So this is this cross-correlation, right? So this is a power spectrum plot again. So this is the total E mode of the polarization. And this is the cross-correlation, this dot last line here. The cross-correlation between the total E mode polarization and the KSC generated at galaxy clusters. We can compute whether this cross-correlation can be measured or not. And again, it's very marginally measurable, right? So if you if you are able to measure or to predict what is the peculiar velocity of all clusters above a given mass, so the y-axis here is the decimal logarithm of the mass of the halos for which you can estimate the peculiar motion. So if your galaxy surface permits you finding out what is the peculiar motion, or predict what is the peculiar motion of all halos more massive than 10 to the 13 solar masses, then you are in this range. You are along this horizontal line. So what is the abscissas? Abscissas is just the decimal logarithm of the signal-to-noise ratio with which you can estimate or predict this peculiar velocity. So if you can predict what is the peculiar velocity of clusters or groups of 10 to the 13 solar masses, a signal-to-noise ratio of 1, then you are in the signal-to-noise regime of, I think it's 4 here, yeah, around 4 or so, right? So again, you need to have a density field that allows you predicting how matter moves very accurately in order to be able to see what is the effect of the missing baryons, right? So this is pretty much what I wanted to tell. So let me just conclude. I presented, I was a bit afraid of not finishing in time, but maybe I've gone a bit too fast. Anyway, this is the last transparency. There are two channels for the CMB to interact with the missing baryons. The thermal Semion-Feldovich effect seems to be caused mainly in collapsed objects. That is where the pressure is the largest. But these environments we know already because there are galaxies there and they emit in the X-ray. So the thermal Semion-Feldovich effect is not going to tell us about the missing baryons we cannot see. So in that sense, thermal Semion-Feldovich effect is not that good when searching for missing baryons. We could use the Thompson scattering and the peculiar motion of these missing baryons with respect to the CMB. This, if quality future data is available in terms of galaxy surface, should tell us about the bulk flux, but only marginally about the missing baryons. And if one combines measurements of the CMB polarization, of the E mode of the CMB polarization, with surveys of large-scale structure, then one should get a different and independent probe for the missing baryons, right? But still, it's in the margin of detectability, right? It's really close in the margin of detectability. So the conclusion is that this is a very tough problem, right? Using these effects, we might get to have a handle on a slightly larger fraction of the missing baryons. But it does not seem to be easy to get a vision of the amount of baryons that are surrounding us and are a very diffuse, non-interacting phase. Right? So that should be it. I'm finished with 2 minutes.
Thank you very much for the talk. So we have some time for questions.
Carlos, if I understood you well, you are doing all your calculations using electrons as the as the missing baryons. What about the other components? So, for example, protons. So how they enter into these calculations?
Yeah, I mean, so you have a plasma. So most of the baryons you cannot see is actually in an ionized state, right? Electrons are the part of the baryons. Actually, they are not baryons, but I mean, they just probably, so the medium is neutral. You have this divide length. The medium is neutral. So you have the protons nearby the electrons. It's just that the electrons are much more efficient when interacting to the CMB than the protons. Okay. So if you want to trace the baryons as a whole, what you do is trace the interaction of the electrons that are close to the protons, because the medium is neutral, with the CMB. Okay. But a priori, everything goes combined. You have just an ionized plasma. So most of the missing baryons you cannot see is just an ionized plasma, which is between 10 to the 5, 10 to the 7 Kelvin. Right? And then you're using the electrons, which are the ones that are more efficiently interacting with the CMB.
And the other question that I have is, you say that having deep imaging survey, you are going to be able to constrain the bulk flows. But I'm unable to understand this. So in principle, would you not need kinematical information? So
that's the thing. So if the theory is correct, once you have a good knowledge, I'm not going to say perfect knowledge because that you're never going to achieve. But if you have a good knowledge of this, of the overdensity, of the matter distribution, if your theory is correct, you can invert this into by the continuity equation or the Euler equation into what the velocity field is. Okay, especially if you're in larger scales where these perturbations are very small, all these equations linearize. So you can easily, right? Easily invert delta, the matter over density or the galaxy over density into the velocity. Then this would give you a template, an idea of how this matter is moving with respect to you and with respect to the CMB. And once you know this, then you can have a template of what the kinematics in Yazel should be, and that you can cross-correlate with the actual total CMB you have, and hope to detect that a cross-correlation between it.
Would it help, for example, instead of having large deep imaging surveys, to have medium deep imaging survey, but combined with the spectra? It will be much better, maybe?
Yes, in the sense that here I'm very optimistic. I'm assuming that that the errors in the redshift, that you know what is the 3D distribution of matter. That means that you know the redshift and you know the angular position of the sky. How redshift space distortions affect the reconstruction of the velocity is something that you have to see. For instance, these future surveys, they need to have a relative accurate redshift determination. The intent of these future surveys, like Pan stars, is to measure the 3D distribution of matter in the universe below redshift 1. So they have typically a redshift accuracy of 1 delta C over 1 plus C is of the order of 2 × 10⁻³ or something for the things that they want to measure. That should be, they do it by either spectroscopically or they are using very many different filters, and they are just by photometric redshift, they are estimating the redshift. But yes, you're right, you really need to have as accurate as possible redshift determination for these objects, because otherwise your inversion into the velocity field is going to be inaccurate. Right? This is far future. This is just looking at, can we have hopes of detecting bulk flows? No. Right? Can we test the theory or not? But for that, we really need high-quality data, both in the CMB side and in the galaxy side, in the large-scale structure side.
Okay. All these effects depends on the electron density.
Yes.
Right. So you should know, you must assume what is the ionization of your medium, which you don't know, and also the metallicity of the medium, which is, again, providing a lot of electrons if you have metals.
Yes. Most of these effects are coming from scales of the order of 10 to 20 megaparsecs. At these scales, I'm assuming that most of the matter is ionized, and you essentially have an electron plasma. Right? So
is this a good approximation?
At scales of 20 megaparsecs, yes. We see that with the CMB, we see that the universe is practically ionized. Right? The universe is practically ionized. After first stars form, you have an ionized intergalactic medium that we know, at least up to redshift 6 or something.
Okay. Yeah. And the metallicity is of concern?
The metallicity, I don't know how it plays here, because what I'm talking about is just the interaction of free electrons with CMB photons.
If you have metals, this will sort of, in particular if you're assuming that everything is ionized, if you have metals, it is not the same if they are singly or, they are sort of trapping a lot of electrons.
Trapping a lot of electrons. So you're saying that the electron density could be modified by the presence of...
By the metallicity.
I haven't taken that into account. So is this important only in the very... I don't know. Is this...
No, I don't know.
we don't know either. Yeah. So it depends. Yeah.
It's hydrogen, that's all. And the same happens with helium, or is?
Yeah, and I guess that metals can only hope to trap a few electrons, like into the sphere like that. You're in the safe side on this one.
Any other question? Maybe I could ask.
Go ahead.
I have the impression it seems difficult to probe the missing baryons, and particularly to separate what is the contribution of objects which are collapsed but are under the detection limit of your experiment, and things like filaments or where we expect most of the baryons. But I would like that you comment a little bit about the first method of detection. You were pointing that you expect at the most 5% of the contribution coming from the, let's say, the diffuse wave.
Yeah, right.
At the most.
At the most.
I mean, that is for direct detection. What happens if you use a tracer? I don't know. If you take a galaxy catalog and you select in density, in overdensity, the number of galaxies in order to trace low density regions, or you select a certain type of objects that might help to trace that. I mean, can you expect to enhance the...
We were thinking about, after we finish this, we're thinking or hoping, I mean, thinking of devising ways to find out the effect of this diffuse phase. But, But, I mean, there are two problems here. First, this diffuse emission, to be important, usually take a large area, right? So the largest the area is, the most likely, the most probable that you have some unresolved group at higher redshift that you don't see, and it's introducing some extra signal that is actually not due to this diffuse phase, right? So that was, I guess, the main problem of the thing, right? Of course, you could try to integrate. If you know that your filament is here, you could try to integrate this. You could try to remove all your resolved halos, biggest clusters, and then integrate on this area, hoping to get a good detection of this filament structure. But then, how sure can you be that behind this big area you don't have small clusters, small or unresolved halos that are actually contributing to confusion noise? Yes. Yeah, but if there is any way, that's one way. Yeah, I guess I agree.
And well, just a final question, just for curiosity. Could you tell us a few numbers just to have an idea of what are the expected yields of the Atacama Cosmology Telescope in terms of, I mean, what number of clusters that you expect to detect and the sky area that you will cover?
Yeah, well, the sky area depends on how well we are doing now. So,
at least nominal...
So nominally we were expecting to cover, there were two policies. So the first, there would be one season where we would go scan deep, but not very wide. And then another strategy where next season we would hope to scan wide, but not shallow, not deep. So, right now we're more worried about other issues, more technical issues. But the hope is to find like one cluster every 3 square degrees or something. So the mass limit is 10 to the 14. We hope that to reach that level.
It covers something like 10,000 square degrees.
Yeah, but that's for the deep. No, this limit is for the deep case, right? 100, around 100 square degrees, right? So if you have like 1.3, it's like 30 or so. It's not many. That's not many. Of course, it depends a lot on the true value of sigma 8. But when this, a few years ago, sigma 8 was larger, and we were hoping to find many more. Now sigma 8 is smaller, and we are finding many fewer. So we don't really know. Right now, we have seen a few of them, but well-known clusters, right? So nothing. We're working on that.
If there is,
maybe I shouldn't have said that.
Is there any other question? If not, just to remind you that Carlos will be here for the rest of the week until Friday. So if you have any other further question about this topic, you can speak with him. He will be around. So thank you very much.